welcome to another module in this massive open online course on Bayesian MMSC estimation for MIMO OFDM wireless communications. Alright. So, what we have been doing or what we have done in the previous module is to describe the MIMO wireless communication system model. Alright. So, we have laid down the system model for the MIMO system. What we are going to do in today's module is to explore it a bit more, that is statistically speaking, derive the statistical properties of this one, more specifically the statistical properties of the channel matrix and the statistical properties of the noise matrix, because these are going to be important for us to derive the MMSE or the LMMSE estimate. Alright. So, we are looking at MIMO channel estimation. And what we would like to do is we would like to examine the statistical properties of the MIMO channel of the MIMO channel and the noise. So, we have the MIMO channel, which is the model, which is y equals x h plus v. This is our MIMO channel model. Remember, this is the model of the MIMO channel which we have derived in the previous module. This is y, which is an n cross r pilot matrix, observation matrix, x, which is n cross m, h, which is m cross r, MIMO channel matrix, v, which is n cross r noise matrix, correct. And what do we have? The various quantities we have: n equals number of pilot vectors, n equals number of pilot vectors, m equals number of transmit, antennas, alright, and r equals your number of receive antennas. R equals number of receive antennas, and H is the MIMO channel matrix. This is the M cross R MIMO channel matrix, and we would like to estimate this MIMO channel matrix, that is termed as MIMO channel estimation. Alright. But before we do that, let us examine the statistical properties of the MIMO channel matrix and also the noise matrix, that is, this is V, which is the noise matrix. Okay. Alright. Okay. So, what we have is, let us write this channel matrix down explicitly. We have H, which is your M cross R matrix. We already seen this is H11, H21, so on up to HM1, H12, H22, HM2, we have H1R, H2R, HMR, okay. And we have also said that Hij is the channel coefficient between Hij is the channel coefficient between ith transmit antenna as per our definition and jth Hij is the channel coefficient between the ith transmit antenna and the jth receive antenna, alright, and therefore naturally we have m transmit antennas, r receive antennas. So, this has m rows and r columns basically, alright. So, it is an m cross r channel matrix. What we are going to do now is organize this as a grouping of rows. So, let us call the first row H1 transpose, second row H2 transpose, last row HM transpose. So, I call this H1 bar transpose, that is the first row, H2 bar transpose, that is the second row, last row is I have m rows HM bar transpose, because each row is a row vector, I am denoting it by the transpose of a column vector, alright, H1 bar transpose, H2 bar transpose. So, I can write this H as equal to a collection of m rows, that is H1 bar transpose, H2 bar transpose, HM bar transpose. For example, that is H is equal to, let me just write this thing over here explicitly, H is equal to H1 bar transpose, H2 bar transpose, HM bar transpose, alright. This is a collection of m rows. For example, you have H1 bar equals, from our definition, H1 bar is a first H11, H12, naturally it is of size r, okay, H11, H12, H1r and so on, okay. So, this is H1 bar. Similarly, one can define H2 bar, H3 bar up to HM bar, okay. So, H bar is the matrix H, which is m cross r, is the collection of m rows, it's H1 bar transpose, H2 bar transpose, so on, HM bar transpose, alright. Now, let us assume the channel coefficients, let the channel coefficients H I j be IID, not necessarily Gaussian, they can be independent, identically distributed with variance of each term, that is expected value of. So, let us first start with the mean, let us assume 0 mean, expected value of Hij equals 0, which basically implies 0 mean. Let us also assume they are identical. So, they have identical variance, expected value of magnitude Hij square equals sigma h square, that is each has identical variance, prior variance sigma h square. Further, since they are independent, naturally they are uncorrelated, let us assume that H, that is any two channel coefficients are independent, Hij, the product expected value of Hij HKL equal to 0 if I not equal to j or k not equal to n. That is, if you look at any two distinct channel coefficients Hij, HKL, the expected value, the correlation between that is correlation between Hij, HKL is 0. The expected value of Hij, HKL, the product is 0. Alright. So, they are both these two, of course, we are assuming they are independent. So, naturally it also follows that they are uncorrelated, alright. So, these two, for if you take any two distinct channel coefficients, the correlation between them is 0, rather the cross correlation between them is the correlation is 0, okay. And now, let us say, now we want to compute this quantity RHH equals expected value of H transpose, which I can write as RHH, which you can write as now. Remember, H is basically your, this is your matrix H, H1 bar transpose, H2 bar transpose, so on up to HM bar transpose times H1 bar, H2 bar, so on up to H M bar. Okay. Now, now look at this, this is H, which is M cross R, and this is H transpose. Naturally, H transpose, this is an R cross M matrix, all right. And now I am going to simplify this further. If you simplify this, this is going to be expected value of, well, H1 bar transpose H1 bar, that is norm H1 bar square, H1 bar transpose H2 bar, that is simply H1 bar transpose H2 bar, H2 bar transpose H1 bar, H1 bar, and norm H2 bar square, so on, and you can write the elements of this matrix, so on. This will be, by the way, product of M cross R, R cross M, this will be an M cross M matrix. This is your R H H covariance matrix, that is covariance matrix of the channel matrix H bar. Now let us look at this. Now observe, right, now we want to compute this covariance matrix by taking the expected value of this matrix, correct. Now let us observe this quantity, expected value. For instance, let us observe and simplify this quantity. Let us observe expected value of norm H1 bar square, this is equal to, as we said, H11 square plus H, well, expected value of H11 square plus H12 square plus H1R square. Remember, that is your H1 bar, we have already specified here this matrix, this vector H1 bar, and similarly you can compute for other vectors also. And expected value of each of these, remember these are IID random variables, each of these quantities has a variance sigma square. So this is, well, basically sigma H square, each of these quantities is equal to sigma H square. So this is sigma H square R times, so this is R times sigma H square, okay, expected value. And similarly this is also equal to expected value of, because all of them are identical, expected value of norm H2 bar square, so on up to norm expected value of norm HM bar square. Each of these is basically equal to your R sigma H square, which means basically if you look at these diagonal entries, expected value of all these diagonal entries, all these diagonal entries will be R sigma H square, okay, that much is clear, okay, all the diagonal entries of the covariance matrix will be R sigma H square. Now let us look at the off diagonal entries. For instance, expected value of, let us look at the off diagonal entries. Off diagonal means off the principal diagonal. For instance, I think again that is also clear. For instance, if you look at this matrix, this is the diagonal or the principal diagonal. When we talk about diagonal, we talk about the principal. Rest of the entries are the off diagonal entries. Alright. Typically the diagonal entries demonstrate slightly different properties compared to the off diagonal entries, as we are going to say. Expected value of H1 bar transpose H2 bar, this is equal to expected value of, well, I can write this H11 H21 plus H12 H22 plus so on. Now, you can say I can split this into the sum of the expectations, that is expected value of H11 H21 plus expected value of H12 H22 so on. And now, you can see each of these quantities, this is equal to 0, where we are using this independence or basically which leads to uncorrelated, that is expected value of H I j into H k l equal to 0 if I not equal to j or k not equal to c. Therefore, all these terms expected value of H11 H21 expected value of H12 H2 all these terms are 0. So, similarly you have 0. So, basically this thing is 0. So, what you have net is all the diagonal entries are equal to R sigma h square, all the off diagonal entries are 0 in this covariance matrix of diagonal equal to 0, and therefore, that simplifies our covariance matrix. Therefore, now we have a nice expression for the covariance matrix, that is we have expected value of H transpose equals expected value of this thing, the matrix that we described above, that is R sigma h square R sigma h square R sigma h square, and all the off diagonal entries are basically 0, that is this has the structure R sigma h square times identity m cross m. So, this is your R H H. This is the covariance matrix of your channel. Okay, R H H equals R sigma h square. This is the covariance matrix of the channel, or this is basically your channel covariance. Okay. Now, let us look at the covariance matrix of the noise, that is expected value of V transpose, because remember to compute the MMSE or LMSE estimate we need two quantities, one is RYY, that is covariance of the output, we need RHY, cross covariance between channel H and the output Y. Alright, in order to compute that we also need some other properties, that is basically the channel covariance which we have computed RHH, and also now the noise covariance which is equally important. Alright. So, the noise covariance again that can be computed in a similar fashion similar to the channel covariance. Consider the noise matrix V consider the noise matrix V, we have V equals, again V is an n cross R matrix, I hope you remember from the previous module, that is V11 V21 so on up to VR1 V12 V22 up to VR2 so on up to VN V1N, that is noise sample on antenna 1 at time n, V2N so on up to VRN. This is your noise matrix which is n cross R noise matrix, alright, and in this Vi comma k equals noise sample on antenna I at time k, alright, noise sample on antenna I at time k, okay. And let us now assume the noise is Gaussian, let similar to previous, let Vik, the different noise samples Vik be IID Gaussian, noise samples at all antennas at all time instants are Gaussian and also independent of each other, which means, and let us assume that they are 0 mean, again similar, follows largely the development of the channel coefficient, expected Vik equal to 0 for all I comma k, expected the noise variance, expected value of magnitude Vik square, this is equal to identical noise, identical, this statistically identical, this independent identical. So, all of them have 0 mean, all of them have power or have variance sigma square, alright, and expected, again they are independent, therefore expected value of Vi, therefore expected value of Vik times Vjl equal to 0 if I not equal to j or k not equal to l. Okay. So, the noise sample, again very simple model, the noise samples Vik are IID Gaussian, they are 0 mean, variance sigma square each, and the correlation between any two noise samples corresponding to either distinct antennas, receive antennas, or distinct time instants, or both is 0. Okay. And now again we can split this into rows. Now you can see we can split this into rows, that is V1 bar transpose, V2 bar transpose, or each row corresponds to a different time instant. Therefore, we can denote this as V1 bar transpose, V2 bar transpose, V bar transpose of n. Okay. So, I can write V, the noise matrix, as V1 bar transpose, I am sorry, V1 bar transpose, V2 bar transpose, V bar transpose of n, collection of n row vectors, naturally it is a n cross r matrix. So, it has n rows, and similar to now I am not going to go to the entire derivation again, because you have considered IID noise elements, you can show that expected value of Vi bar transpose Vi bar, that is expected value of norm Vi bar square equals R sigma square, where sigma square is the noise variance. Similarly, expected value of Vi bar transpose Vj bar equal to 0 if I not equal to j, alright, and therefore the noise covariance RVV, the noise covariance, this is similar to what, so therefore the noise covariance is expected VV transpose, which is equal to expected value of V bar transpose 1, V bar transpose 2, V bar transpose n times V bar 1, V bar 2, V bar n. Again this will be where the off diagonal elements are all R sigma, the diagonal elements are all R sigma square, the off diagonal elements are 0. So, this will be R sigma square I, but this will be an n cross n identity matrix, because look at this, this is an n cross R matrix, this is V, which is R, this is V transpose which is R cross n, therefore V transpose is n cross n. So, this R sigma square identity n cross n, and this is RVV which is your noise covariance. So, this is your noise covariance matrix. This is your noise covariance matrix, alright. So, what we have done in this module is basically we have explored the statistical properties of the MIMO input output system model further. Assuming IID channel coefficients, we have derived the channel covariance. Assuming IID noise covariance, IID Gaussian noise coefficients, we have derived the noise covariance, alright. And now we are going to use this in the computation of the MMSE or LMMSE estimate of the MIMO channel matrix subsequently. So, we will stop this module here. Thank you very much.